This is finally the last video on elements that are important to industrial applications, whether it be polymers, smart materials. And we've talked about, if we kind of just quickly review, how size of the atom or ions in the periodic table change. Usually they get bigger as you go down, whether it be ion or atom. Usually get smaller as you go across, but it didn't seem to get small real quick in the D block region. The natural form, we talked about the halogens specifically, kind of went through gas, liquid, solid. Most of the metals are metals, they're solids. Non-metals can be, I guess, gases. They can come in nitrogen gas into, can also come in solid form like carbon or sulfur or phosphorus. And we talked about the abundance and how there's a lot of different elements used to make smartphones that come from the S block, the D block, the lanthanides, which were down below the D block, and the P blocks. They're just coming from everywhere to get the properties you need. And that's what's really cool, is that atomic structure, and you might say molecular or metallic structure, drives properties. That's why we have to go to different places in the periodic table to get the properties we need. And we looked at transition metals, and I really focused again more on the organic chemistry that you can do with transition metals, not just the properties of strength, but we did look at metallic glasses, which are just dang cool in how they bounce in little balls or beads so long. And we looked at heterogeneous catalysis, where we have some solid surface that organic molecules lay onto. And we sort of became a little cloudy, though, because we saw you could have some nanoscale surfaces, platinum or palladium, that we coat with silver. Then we talked about homogeneous catalysis using either palladium, the titanium, and the biggest deal is that on that metal center, if my little pen or the marker top would be the metal center, is we can have two carbons combined to it, and then this is cool. Two carbons bonded to a metal can slide together and leave in a reductive elimination. And you need to know, only metals are good at that, where they can bring two R groups, carbons, and make these kind of bonds, and do it very, very quickly, and do it in a very controlled way with regioselectivity and stereoselectivity. It's just exquisite, might be the best word for what metals can do in organometallic chemistry. And that was kind of deep. I hope you got through a little bit of that. And then we looked at just one example, the cuprates, using copper as a metal surface, and how we made it from organolithiums. We can make cuprates and such. And that was the third video. And we're finally going to get to, you can't see it here, is that P block, the P block. And really, if you think about it, the two that you really want to remember, along with, I guess, carbon, is nitrogen and oxygen. If you think a lot about your organic compounds that are in the body, or biochemical compounds, a lot of them have H, C, N, and O arranged some way in that structure. For just hydrocarbons, lipids, even they have a little bit on the end of a polar group. And if you look at your amino acids, there you go. You make your amino acids from these four elements. So are these important, these nonmetals? You bet. We don't have the protein structures without the amino acids, and we don't have amino acids without H, C, N, and O. It's really cool, some of the things you can do, of course, looking at the nonmetals. I did need to cover one topic and how to find oxidation states for metals. So I want to kind of quickly review this. If you have a element such as this zinc, Cl2 or H2, their oxidation state is always zero. In their elemental form, we consider them to have a zero oxidation state. Now remember, they can be a negative or they can be a positive. If I had two chlorines in this state become reduced, meaning we get a negative charge, we get electrons to them, then of course each of them would have a -1 oxidation state. And the zinc, let's say it had to give the electrons to chlorine to make Cl minuses, then he would have a +2 charge, and his oxidation state is equal to his charge. That's the second bullet here. So zinc, if he gave the chlorine those two, remember the 4s electrons, transition metals can often give up 2 electrons in the 4s orbital, those first row transition metals, we would say then his charge is his oxidation state, or oxidation number. So of course sodium has a common charge of +1. Can sodium be used for organometallic chemistry? I hope at this point you're saying No. Sodium is not really used in much in organometallic chemistry. Its brother in that same column, but one step up, lithium is. Calcium, is it used in organometallic chemistry? I hope you're saying no. But its brother, one step up, magnesium is. Remember, these were mostly used for inorganic chemistry. They can combine with oxides or phosphates, sulfates, nitrates, things that are more water soluble. All right, last two bullets. Hydrogen typically is +1. Now, there is one exception to that. If you have lithium hydride, which is a really cool substance, it is dang sensitive to moisture, like on a hot summer's day. You don't want to leave this out. Because we know lithium is not very electronegative, so it's not a full positive, but you can consider this bond to have a little bit ionic character, and the hydrogen is called hydride. IDE is given to things that are negative. So this would mean that hydrogen has not a zero oxidation state or a +1, it would be actually -1. So there's some exceptions to hydrogens are always +1, you just saw it, but they're usually +1, and oxygens are usually -2. Of course, if it's in the elemental form, the oxidation state would be 0. But in bonding to things, even here, here, you'd say its oxidation state is -2. Let's apply these rules to just two metals. Now, if you look at this silver here, something to notice is that we have a nitrogen that's bonded to that silver with no charge shown. That is so important. If you see a nitrogen in an ammonia, NH3, bonded to something, and it's not showing the charge, that means it's serving as a ligand. Well, that means it doesn't change the oxidation state of silver. So whatever it was before the ligands came in on it, it was after the ligands came in on it. So they're telling us what it is. They're saying this silver has a +1 charge. So guess what the oxidation state would be? +1. This is important. This is a complex or coordination compound. Coordination compounds have ligands. They're not always neutral. I don't want to want you to walk away thinking ligands are always neutral. You can have sometimes cyanide as a ligand. You can have water as a ligand. I'm going to focus mostly on the neutrals because that's sort of weird to students to see ammonia or water binding to something as a metal but not being shown a positive charge. We've shown it here, and so we can say, oh, that's not a ligand then. It's got a bond that's been made, so it's given that positive charge. But these ligands, you could have water. Now, most of your organometallic reactions don't want to have water present, just so you know. We're working on getting them to be more water friendly. The body does everything in water. But typically, most of these homogeneous catalysis compounds are not suitable in water. But maybe you had some, I don't know, ether or something like that that bonds to the metal. And it's given an L symbol saying it's just a ligand, not a full bond. This would also be a bond. So this carbon is bonded to that palladium, not through a coordination, but through a covalent bond. I said I was going to do one more. So let's look at that palladium then. Now, if we just said these are ligands, that does not affect the oxidation state. But this carbon and this oxygen are pulling electrons. Anytime you're bonded to a metal, a carbon, a nonmetal to a metal, nonmetal to a metal, he takes the electrons. So right there, these two electrons are cheating towards the carbon. That's taking one away from palladium. That's +1. But so is the oxygen. It's pulling away, so that's +2. So the palladium here is a +2 state, is a +2 oxidation state. As you guys, as you know, in this reaction, it turns out that when these two get together, the palladium reacts with the borate, you can have a ligand exchange or a exchange of that oxygen, and you get two phenyl rings that'll come together. And in the end, what you'll have is that palladium and the two ligands left. Well, when that happens, and this has the reaction between the benzene ring and the benzene ring, and they reductively eliminate away, you'd be left with this form of palladium, which actually has an oxidation state of 0. So it's the metal with two ligands around it in an atomic form. It would have an oxidation state of 0. So this reaction goes between palladium having a +2 oxidation state and palladium having a 0 oxidation state. It just cycles back and forth as it goes through the reaction. Really cool stuff. All right, almost done. This will be hopefully the shortest video of the 4. So looking at the nonmetals, this is carbon, this is nitrogen, so you'd have carbon and nitrogen going underneath, and everything else. And of course you go through that metalloid zone, so I need to talk about the metalloids as you go down from in group 4 and in group 5 you run into that diagonal metalloid. But remember, carbon is huge when it comes to organic chemistry. It is the backbone, literally, of our structures. And I know we have phosphate linkages for DNA, but everything else as far as lipids and amino acids involve carbon, oxygen, carbon, nitrogen bonds. They're very, very important. And they're so versatile because they can make sigma and pi bonds. You can't do that with silicon, and not so easily with sulfur. Phosphorus, they're kind of more in the 3rd row. They don't do pi bonds very well. But carbon can do sigma bonds, pi bonds. It can make 3 bonds to be a positively charged element. It can have 3 bonds and have a negative charge, like you saw with the organolithium reagents. So carbon can be partially negative, it can be partially positive. It has a lot of flexibility. So silicon is not able to make pi bonds. That's the next one under carbon. It can have more than just 4, bonds, because it has those d orbitals it can make use of, and that's important for catalysis. That's important for semiconductor properties. Silica is most prevalent. It's like the most prevalent type of rock outside of aluminum oxides. You can have silicon oxides in a lot of different types of rocks. All right, we're moving on to the 5th group, or the 5th column, main group, 5A. So phosphorus, nitrogen, and then phosphorus. So they can serve as ligands. If we, I remember a reaction where we had a, we had a phosphorus oxygen double bond, and we had 3 phenyl groups are off this phosphorus, and we used a ligand. In our case, it was a trichloroborane, and it had the ability to accept those lone pairs from this oxygen on a triphenylphosphine, and it would accept those. You can do that. This would be kind of a Lewis acid. I'm using a lot of terms. It means it's accepting a lone pair. These would be more like Lewis bases. They have lone pairs to give. That's a very common thing with those group 5A elements, is they have, and remember this, the group 5A have more of a Lewis base effect. They can give their lone pair, their 1, to somebody who is lacking in electron density, whether it be a boron center or whether it be aluminum. Aluminum, if I put it right here, aluminum would be one that has only 3 bonds off of it. Aluminum trichloride, for example, that's a terrible chlorine, would be a Lewis base acceptor. And something else we can do with these 5A elements is they have, again, they can make bonds, but they have an extra electron they can give in the silicon network, the silicon chip. And boron has a hole. It can't, I guess what we're doing here is we're using, since it has 5 electrons, we can have these 2 extras, and this one only has 3 electrons, boron, or you can also use aluminum here. Would be some other ones. I can't remember. I think there's a couple other choices you can use for a p-type doping. But boron has less electrons, and so you end up having the inability to make a full bond tetracoordinated with the other silicon atoms. So just know, I guess, in general, that silicone, Si, chips, can have the group 5A elements added as a doping agent, or we didn't talk about this much, but a 3A. So it can be phosphorus or boron that can be used to make this more conductive. It makes the chip more conductive. Well, that's about all I have to say. We know that oxygen is the most abundant element in the Earth's crust. We get a lot, again, silicon oxides, aluminum oxides, carbonates, phosphates. Basically, a lot of your metals are in some oxidized form, other than maybe like your silver and gold and platinum and palladium. There are some what we call native, they keep their native form. So we have some, of course, oxygen in the earth, but we also have in the environment, in the air we breathe. And the combustion of all living things involves oxygens. Ozone up in the upper atmosphere is very important for protection from our ultraviolet light. We have a plus charge and a minus charge. Sulfur is found in a lot of compounds that have a lot of strong odors with them. They have weaker bonds, so they tend to be labile. You can make them and break them like in your proteins. You can make disulfides from those, so they're not as strong a bond and they can't make pi bonds. Let's see, and I think that's about it. I did want to finish with a little story. This is it. Of one more organometallic reaction that's really cool. So they can take this copper bromide, and this is an ionic compound. So if bromine's bonded to that, it's not just a ligand, and it has a -1 charge, and this is +1. What would the oxidation state of this be? I hope you're saying its charge would be, its oxidation state is +1. So what you can do is you can take this bromine in the presence of copper bromide, and this happens in a equilibrium. The bromine can come off with one electron, one of these two, not both. And it takes another one from the copper. So the copper becomes +2. It's stolen. The bromine doesn't take both its electrons away. It's kind of unique. Typically it breaks away and takes both. But the copper mediates the breaking of this bond kind of homolytically. So that carbon-bromine bond breaks like this. And I'm not drawing the rest of the structure here, but the carbon right here has this bond to bromine with 2 electrons. It keeps one and has the rest of the structure it's connected to. And the bromine walks away with 1 electron, connects to this copper, steals another one to make that bond, so the copper goes between a +2 and a +1 state as this reaction proceeds. And you do have to make some sort of ligand around this copper to help mediate this reaction. So this would be a triamine ligand. And remember, do these nitrogens, when they bond to the copper as a ligand in coordination, not in covalent bonding, do they have a charge? I hope you're saying no. That's the difference between a ligand and a covalent bond to that metal. All right, well, that's about it. It's an equilibrium between, I should have 2 arrows. It really cheats towards this form of the bromine, but a little bit every now and then leaves this carbon with what's called a radical, and boy does that have reactivity. It starts unzipping the monomer, making polymer. This is some chemistry that Matuszewski came up with, and it's called ATRP, atom transfer radical polymerization. It's really cool. They may have given it a different name in the last few years because they thought it maybe is not as precise, but it used to be called atom transfer radical polymerization. Well, thank you so much for watching this 3 or 4 videos on elements from the periodic table. Hope you've learned just a little bit, but more so, I hope you've been somewhat inspired that there's a lot of chemistry that goes well beyond what you see in a general chemistry textbook. That's more exciting. It's always changing, developing new materials. It is some cool areas to work in. Thank you. Bye.